Thanks. So, yeah, we just introduced Langlands dual groups. Yeah, so maybe to make the parallel with the reductions that we have for smooth representations of reductive groups. Let me remind you about parabolic subgroups of the Langlands dual group. So it's just a subgroup P such that P surjects onto gamma, and P0, which is defined as the intersection with G hat, is a parabolic subgroup. And then, in fact, it's P is determined by P0, and well, we have a similar story as for regular reductive groups. So up to G hat conjugation, we may assume that P0 contains our Borel subgroup B. And so parabolic subgroups of LG up to G hat conjugation correspond projectively to gamma stable subsets of delta or delta V. They're in bijection anyway. And you can deduce from this that there is a natural map like this, embedding from parabolic subgroups of G up to G of F conjugation into same for LG. And this is surjective if and only if G is quasi-split. Okay. And then for P with the Levy factor M like this, with the corresponding calligraphic P in LG, we have an embedding like this. So factoring through P. And okay, a fact which, well, surprisingly, it was not stated in Borel's Corvallis paper. So the G hat conjugacy class of iota P only depends on M. So the notation will be iota M, and the images of these iota M's will be called relevant Levy subgroups of LG. So this fact in the case of GLN is a triviality, but okay, and actually you can, well, I'm skipping it, but you can define Levy subgroups, well, Levy factors of parabolic subgroups of LG, and they're this. well, the relevant Levy subgroups are examples of subgroups, and as in the case of Levy subgroups of G, you can also describe them as centralizers of tori. Okay. And I'm going to waste a bit of time discussing different versions of Veil-de-Lin groups. So the Archimedean case is simple. There's just a Veil group, and by convention, the convention is just that the Veil-de-Lin group is the same thing. So now assume F is non-Archimedean. Okay, so I hope you remember what the Veil group is. I think you do. So we have two versions, or three, but let me just mention two. So this WF prime, which is, so you take a semi-direct product like this. So the additive algebraic group with action so this GA is over C or Q, if you want. With this action, so here I'm using Artin reciprocity. So there are two choices anyway, to define the norm on the Veil group. The second version is the one that we will really use, and that's just this product with SL2. So again, it's algebraic group SL2 over the field of coefficients C. Say. And when C is the complex numbers, you can also have SU2, topological group SU2 here. And we have so different notions of Langlands parameters. Let me skip the Archimedean case. Because it's simpler. So the version with one, well, let's call them Veil-de-Lin Langlands parameters. Is so you take a row like this, continuous, semi-simple, and such that the projection, well, the map to gamma gives you a commutative diagram. And an element n of the algebraic, so Lie algebra of G hat, such that we have the following relation. Okay, and so the point of this definition is that this is natural when you consider L-adic representations of the Galois, the absolute Galois group of F, by the, that's essentially so minus the semi-simple condition here. That's what comes out of the L-adic monodromy theorem. And for the second version, so that's what we will call Langlands parameters. So it's similar, but now it's continuous semi-simple on the veil group and algebraic. So this should be SL2 of C if you want. So algebraic on the SL2. And the relation between the two is quite simple, but let me make it explicit. So if you start from phi Langlands parameter, and you can compose with, okay, everything is called iota, I'm sorry. So iota W, so you map W to this thing, and you get upper row n, which is, so you compose phi with this iota W, and you differentiate the algebraic morphism on SL2, take the image of this thing. So this I'm going to call phi semi-simplified. So it's a bit, okay. Wait, so it's really what happens when you semi-simplify an L-adic representation. That's the origin of the terminology. And essentially by Jacobson-Morozov, these are really the same thing up to conjugacy by G hat, sorry. Okay, and well, there are reasons to prefer one or the other depending on the context, but we'll mainly use just the veil group and sometimes the semi-simplification. All right. So then we have, well, parallel to the classification, well, to the reductions in the theory of representations of reductive groups. We have reductions, so there is a Langlands decomposition that's similar to the Langlands classification for parameters. And that's really something like just a polar decomposition. So you can write any parameter canonically like this, where phi 0 is bounded on the veil group. Yeah, sorry, so maybe just to be explicit, from now on we only use WD, so the version with SL2. Okay, so yeah, you have a kind of polar decomposition where you just write parameter canonically as the product of something bounded and something positive real valued in some sense. And you can actually check, so from this you also get a canonical parabolic subgroup, and you can check that this is really the same formalism as the Langlands decomposition, sorry, the Langlands classification, so the thing with J P sigma nu, although it's not completely obvious. Some character, yeah. I'm not being too precise here.
Is this unique?
Yeah. Phi 0, chi, and there's also a parabolic that you can throw in there, or just canonical datum that you. Yeah, so the reference is surprisingly recent. I think it's 2014. There's a paper by Zilberger and Zink. And we have also the following fact. So, so let me take this opportunity that, so we call such a phi 0 tempered. That's really the analogous thing. And so we have the following fact. If you have a Langlands parameter, then the set of Levy subgroups of LG such that 5 factors to which are minimal for the property that they contain the image of phi. Is just one conjugacy class under the centralizer that I will denote in G hat of phi, that I will denote by S phi. And so that's really the generalization to arbitrary dual groups of the decomposition into a direct sum of irreducible representations in terms of, in the case of linear representations. Where did the eraser go? And we call phi discrete if this Levy M is as large as possible, so LG, just LG, and that's equivalent to this S bar phi defined as the, so this always contains this subgroup here.
There's a question on this call that asking non-dual group, algebraic group, or C points of an algebraic group. I guess it's C points, right?
Yeah. I said this morning I will abusively identify just the C points and the algebraic groups. Also, there's a semi-direct product with some infinite group gamma, and I'm not being too precise here, but you can take a finite quotient or maybe I should have said essentially discrete here, but okay. So it's the thing that should correspond to essentially square integrable representations.
Can I clarify something? So we're defining tempered to be those things that have bounded image under WF, that's the definition. And then the fact is that, what is the fact? And kind of pressure well. That if you take a minimal Levy containing the image, then...
So the set of Levy subgroups which contain the image, so through which 5 factors, and which are minimal for this property, is just one conjugacy class under the centralizer. So it's essentially unique.
Yeah.
So sorry, this boundedness is like, that's not an algebraic property now, right?
Yes, so as always I forget. So anything related to Langlands classification here needs to have C, for C, the complex numbers, you're right. Yeah. Okay, and call phi relevant if this M is relevant. So this is not calligraphic for some maybe M of G. So again, up to G hat conjugation. Okay, can finally formulate a conjecture. So there should exist maps. So for any G, LL, maybe I should have put LL in the from smooth irreducible representations of G of F to so that's Langlands parameters up to G hat conjugacy. Satisfying the following properties. So we will denote pi phi of G for the fibers. Maybe I should use the sideboards. I'll change. Okay, so if G is a torus, so is commutative, then this should be the bijection obtained using a local class field theory. So in the case of a split torus, it's literally the Artin reciprocity map. And in general, you have to work a bit with a co-restriction too. But it really follows from local class field theory. So the fibers, or the L packets, should be finite. And the image of LL should contain at least all discrete parameters. And I'm actually not exactly sure that this is true if F is the field of real numbers. I'm not sure, well, but it can be checked at least in principle. For G is a product, well, we should have the obvious thing that you can imagine. The point of this is just to make the next point more useful. So if you have a central isogeny, so recall that this is surjective with a finite central kernel. So then we have a theta hat, or maybe that was L theta. So for any representation for H and any, let's say, pi prime occurring in the restriction to G. Yeah, so this restriction is always a semi-simple finite length. We should have the local Langlands parameter of pi prime should be just a composition. Okay, so we should have a compatibility with the veil restriction. So I'm not giving details here, but so when you form the veil restriction for some extension, some group over an extension E of F, then well, the points over E of the original group and the points over F of the veil restriction are the same, and so you should have the same thing, and you can check that the formalism works on the dual side, and this should be compatible. So pi should be essentially L2 if and only if the parameter is discrete. And then we have compatibility with our reductions. So take M Levy of G, and sigma representation of M with a unitary central character and essentially square integrable. Then for any so sub-representation, so irreducible sub-representation pi of the induction. So any induction P does not matter here. That's how we obtain all tempered representations, remember. We should have that the parameter for pi is just the composition with the embedding of Lm inside Lg. And then we have something similar for the Langlands quotients J, P, sigma nu. Again, from sigma tensor nu, you get a local Langlands parameter and you compose with iota P. You don't need to know that the conjugacy class doesn't depend on P now. Okay. We have more compatibility properties. So for F isomorphic to R, or really by compatibility with veil restriction that covers the complex case as well, this should be compatible with infinitesimal characters. And well, you'll have to look at the notes because I'm not giving details here. And the analogous thing in the non-Archimedean case is the following. So let's say, as usual, P is some parabolic, sigma irreducible smooth representation for M, and pi an irreducible subquotient of the induction. Then we should have that so this time the local Langlands parameter of pi is not determined by that of sigma, but its semi-simplification is.
What is sigma here?
Any irreducible smooth representation of M, and actually you can reduce to the superhospital case. There's no loss of generality.
Which that means restriction to the baby.
Sorry?
Semi-simplification means just restricting to the beta group.
It's what is up there. So you just compose with this iota W. It's not a semi-simplification. Yes, sorry, I used the same notation on the side of representations for the usual semi-simplification. Okay, and finally the...
Well, if you use the other version of the tail group, the tail group, right?
Yeah, if you use the first version with the nilpotent n, I didn't say it's nilpotent, but it is follows, then it's an actual semi-simplification, yes. In fact, it is, if you go through the L-adic monodromy theorem, it's really the semi-simplification of the original L-adic representation. So still non-Archimedean, and if the parameter phi is supercuspidal, meaning that it is discrete and that its restriction to SL2 is trivial, then any element of the packet should be supercuspidal. And okay, that is not an equivalence.
And there's a question on Discord. He said he's confused with 7 and 10 because he thinks the local line correspondence is only depend on sigma, inducing them not on pi. Is that true? I think.
So we don't have the same assumptions in. So the question is about the relation between 7 and 10, I guess, because I said that local Langlands of pi is not, the parameter of pi is not determined by that of sigma. And the answer is that we don't have the same assumptions here. Here we have something unitary and essentially L2, or we could have taken tempered, that would work. But here there's no assumption on sigma. So in particular, the central character is not unitary. It's not necessarily unitary.
In the number 8, if sigma is tempered, then not all the irreducible constituents of the parabolic inductions are determined in this way, but only the Langlands quotient is determined by this rule.
One is 8. Yeah. So it's local Langlands of this Langlands quotient is the composition like this. Yeah.
Excuse me. In item 2, is there something about being relevant?
Sorry?
In item 2, is there something about being relevant?
So the image, so that's, well, no. Well, that's, okay. Let me remark on this in
Relevant is whether it's healthy or not, right?
It follows from this list that the image is going to be exactly the relevant things.
But when you say it should contain all discrete parameters, the statement reads the image of LL for a single G should contain all
discrete parameters.
But for a single G, or do you run over inner form?
No, for a single G.
Discrete parameters are always relevant.
Yeah. The 10 is just MG, right?
Sorry, yeah.
Yes, I could have said instead that the image is exactly the set of relevant parameters, because when you go through these reductions, that follows. Okay, so now for a few remarks. So 3 and 4 imply compatibility with central character. we choose the right isogeny, and also with twisting by characters like this. So there's a natural map from this to this that Langlands constructed, and okay. So that's maybe one. Two is that, okay, so everything reduces to be essentially L2 slash discrete case. We have the same kind of reductions on both sides. In the unramified case, it's compatible with the Satake isomorphism. So you could put it in the list of requirements, but it actually follows from the, so it's not obvious, but it follows from 8. Well, the tempered case is easy, and the general case follows from 8, and it's a bit subtle, funnily enough.
In 8, do you really like pin down the Langlands parameter, or only determine it up to semi-simplification?
No, yeah, that's the actual Langlands parameter, and that's maybe the not so obvious thing when you try to prove compatibility with the Satake isomorphism. You have to show that when you have when you take a sigma here that's unramified for an unramified character of a torus, that the Langlands quotient is the constituent which has invariance under a hyperspecial compact subgroup, and not something else in the kernel.
What's the lead in this the classification? Can you repeat the question?
Which one?
The last one.
They cannot hear on the back. Okay. So you could state compatibility with the Satake isomorphism directly, but it actually follows from this. I'm just.
I mean, this is the classification of unramified representation.
Yes. You know that unramified representations correspond to unramified parameters, and actually everything is consistent because this follows from these more general principles. Okay, and the next mark is a big one. So from the compatibility with semi-simplification, you can actually extract another conjecture, and the point is that it's almost no longer a conjecture. So you take as before C and a square root of Q, and there should exist something like this. Which is really, should just be LL composed with the semi-simplification. So satisfying Okay. 1, 3, 4, and analogues of 10 and 11. And so these maps, so the maps LLSS should depend. They depend on G and C and the square root of Q, and this should be algebraic. So functorial in C and square root of Q. Okay, so you can try to remove the square root of Q's if you like, but okay. So the point is that except for functoriality, so I stated this as a conjecture, but this is actually a theorem of Genestier-Laforgue in the positive characteristic case, and Falk-Scholze in general. Yeah, I'm cheating a bit, so it's yeah. So C is Q L bar, and a priori it depends on L. Yes. Okay, so there are more things to say about what you could try to do in the other direction.
Did you explain what semi-simple parameters means?
So that's actually semi-simple, in the usual sense. Sorry. There's no SL2 or...
Yeah, so what does this mean? If it lands in a parabolic, it lands,
yes.
it lands in a levy, right?
Yes, yes.
So it means the image lies in the semi-simple part.
Olivier, could you always try to repeat the question?
Yes. So the question is, what does semi-simple mean for a map from a group to LG? And well, the answer is the simple, not very satisfying answer is you take a quotient of gamma to have a finite group, and you then embed LG in some GLN, and then semi-simple means semi-simple. Okay, it's not the best. There's I think it's a Bourbaki seminar or something by Serre on semi-simplicity for morphisms like this. So that's a good reference. Okay. Yes, so about cuspidal, supercuspidal parameters. So yeah, the only thing that I want to say is that I want to emphasize that this is not an equivalence. So in general, there are supercuspidal representations whose parameter is not trivial on SL2, and that's, well, complications.
Sorry, one quick question. Is the LLSS over there the same thing as the LLSS over there?
It's not, almost. Yeah. So the question is, what's the relation between this LLSS and this LL of pi SS? And the relation is that the first conjecture implies the second. So you can take LL of pi and compose with iota W, so that's this thing here, and call this LLSS of pi, and that gives you the second conjecture. And so because this is now a theorem, well, functoriality would be nice, but this is already a lot. The outstanding question is, how do you go from the second conjecture to the
Even conjecture 1 implies conjecture 2, do you get the functoriality part?
No. So yeah, okay, no, you're right. yes, conjecture 1 is really about when C is the field of complex numbers, because that's when tempered, etc. Yes.
Except for functionality, is functionality on the field, right? Is that?
Sorry?
Yeah, this except for functionality, you mean functionality?
Yeah, functionality on the field. Yes. And actually, yeah, it follows also from these requirements that you should be able to give a purely representation theoretic characterization of essentially square integrable representations, because the exponents that occurred this morning should actually be rational. So them being a finite linear combination with positive coefficients of simple roots makes sense if they're rational.
Can I ask another question? Yes. The question is also from the list of property, does it say anything about the relation between pi and pi and the contract region of pi, the L parameter?
Sorry, which one?
Does your list of property have any implications about the L parameters of the contract region of pi?
It's in the notes. Yes, but this is a question that has several answers. So something that I didn't really mention is that there's more than one local Langlands correspondence, because there's already more than one Artin reciprocity map, and that's related to this. And but I put their reference in the notes. It occurs multiple times. Okay, and then so maybe the last remark is a bit disappointing. Is just to say that this list of requirements is far from characterizing the local Langlands correspondence. Because if you think about it, it's just essentially proving local Langlands is, as stated like this, is just saying that two sets have the same cardinality or something like this. So it's not very hard. So what I'm not telling you here is how to characterize the local Langlands correspondence. And so there are different ways to do this. So in the case of GLN, so which was proved by Enya, Taylor, and Scholze, the characterization is by L and epsilon factors for pairs, and also by local global compatibility. You can ask about compatibility with base change. Okay, yeah, I'm not saying too much. And so we finally come to the second part, which is the refined local Langlands correspondence for quasi-split groups. And okay, so of course we assume that G is quasi-split in this section. So it's interesting to try to understand better the fibers, so the like the size or how the different packets are organized. So first, just because we're curious, but there's actually an important global motivation behind this that I think Tasho will talk about next week. So it's important to understand what's inside the L packets. And yeah, I think I have everything. So the conjecture is that for any Langlands parameter phi, we should have an embedding of the L packet in the set of isomorphism classes of irreducible representations of the group of connected components of this S bar phi. So is it still on the board somewhere? I'm not sure. Yeah. So we call that S phi is the centralizer of phi in G hat, and S bar phi is the quotient by the invariance under Galois in the dual group. And for F non-Archimedean, this should be a bijection. And so actually this thing here is not canonical, it depends on some additional choice, and that's Whittaker datum. So because G is quasi-split, has a Boole subgroup, which you can write as TU, and you choose a generic character of U of F. Yeah, so maybe the field is complex numbers now. And what I will denote by frac W is the pair of U and this theta. And that's the Whittaker datum. But okay, it really only matters up to conjugation by G of F. And this thing here should, sorry, that's another iota W, but should depend on this iota W. And the conjecture of Shahidi is that for any tempered, yeah, so I should have mentioned earlier maybe, we can, it's, because things are so rigid in the Langlands classification, it's easy to reduce to the tempered case, actually. So for any tempered phi, there should be a unique generic pi in the packet, where generic means that there exists a non-zero linear form like this, such that lambda of pi of u v is theta of u, lambda of v for u in u of f. Sorry?
What does generic data mean? Restriction to positive root subgroups?
Generic, theta? Yeah, I'm not, it's in the notes. Yeah, so it's just, it implies non-trivial, for example.
Yes.
What is TU?
So B, so that's a Levy decomposition of B. So I don't need T anyway, so U is the unipotent radical of B. And you cook theta from the simple roots, essentially. Okay.
Sorry, could you clarify, how does the conjecture depend on this choice of Whittaker data?
I didn't clarify yet. I will. Okay. So let's just introduce notation then. So we now want to characterize these iota W, and so what can we do so if you start from phi and s, you can construct two things. So let's just introduce this notation. So you take the trace of this irreducible representation of this finite group, and you take a linear combination of the High-Chandra characters of the elements of the packet. So that you can see this as a function like this, and a special case I didn't finish Shahidi's conjecture. Sorry.
Lambda there is just a function.
It's just a linear, linear. And so because you have base points, obvious base points on the two sides, the conjecture is, of course, that they are. So this should be the trivial representation of the centralizer. And the special case is when s equals 1. And
what is the upside by the bijection?
Sorry?
What is the upside or iota w?
Iota w is this, this bijection. So sorry, I went back. I said that we should have this thing, and I said actually it depends on w. So s theta phi is this thing. So it's kind of implied that it actually doesn't depend on w. Yes, and I don't think I'm going to say anything meaningful in 2 minutes, so I'll stop here for now.
Okay, we have some time for questions.
I have a question. You say that if you just say these properties, then it would be quote-unquote easy to see because it's just the same cardinality in air quotes. But is it that easy?
No, it's not easy. So
is someone able actually to make a map with these properties even just
with the cardinals? Yes, it's not so hard. Well, especially since
with all these compatibilities.
The point is, because you have the compatibilities on both sides, you really only have to do the. Okay, maybe this thing here is a bit tricky, but the rest is it really reduces to the discrete case.
And there you just have to see that the sets have the same cardinality.
Yes, and in fact, I mean, as soon as you have a split torus in the center, the cardinality is that of the reals. So, I mean, you have to show that there is a discrete series representation, but you can take the Steinberg, or you can prove that there exist supercuspitals, which is harder.
In the statement of this conjecture here, what's the logical relationship of the part in parentheses? Is that part of the definition of W generic, or?
Yes, that is the definition of W generic.
But the part in parentheses doesn't say anything about W.
It depends on theta. So theta is part of W. And U is in U of F. Well, actually, it depends on the whole of the
For the local character part, are you working on quasi-split groups or general groups?
This here? Yeah. So here G is quasi-split, but we will try later to have a similar definition.
Is there a conjectural description of the representations as outbound or trivial on wild inertia?
You should ask someone else. Probably someone knows. Well,
maybe you repeat the question.
So the question is, can you characterize the representations whose parameter is trivial on wild inertia?
Should this be depth 0?
Well, it depends which version of the parameters you take, maybe. So you... is it? So he said wild inertia.
Well, depth 0.
But depth 0 would be with monodromy. Do you have really all the same parameters?
And it's conjecture.
We can make this.
Okay. So you don't need anything about the transfer maps to characterize the local Langlands.
Sorry?
The transfer map.
There is one more lecture.
For the crude local Langlands type.
Sorry?
For the crude local Langlands type.
There is no, I didn't, well, I should have written it down, maybe. I didn't give a characterization, and that's a problem. There is no single characterization of local Langlands. There are many cases in which this is proved. Well, something more is proved. But it's not always the same characterization. Well, that's also the beauty of the subject, I guess. But
Can you be more precise on this goal? So goal is to characterize this rho u, and then you define this function, right? And that's always a function you can define. Then when you say the goal characterizes this, we want to identify the function? Is that the...
yes. The goal will be
to repeat the question.
So the question is clarify the goal, and what we'll do next time is explain how this should be obtained in an explicit manner from these seemingly simpler objects for endoscopic groups.
Okay, maybe one more question.
That was my question.
That was your question. Okay, one more question there.
I wonder, like, can you deduce from the probability of central according to, like, can you say something about the local lines for S or N? So does this follow from G on this?
Yeah. The relation, so the question is, what's the relation between SLN and GLN? And yes. But this is here. You can deduce from the.
So you can use this to compute the L packet for SLN.
Yes, but then the interesting question is, what do they look like? And for GLN, I should have said also this S phi is always connected, so there is the conjecture is that the L packets are just singletons, so there is no more than this conjecture. But for SLN, there are interesting things to say. Yeah.
Okay, so maybe we'll reserve the other questions for the question and answer session, and we'll thank Olivier again.